Hi, welcome to this course. This course is about fabrication techniques for MEMS based sensors from clinical perspective. So, when we talk about clinical research, right, what does that mean and how it is really useful. So, there is a saying which goes like this, that the solution for the big problems lie in small things. That is true for our actual life as well as in case of research. When we understand the properties from the micro and nano perspective, we can really understand what lies, what kind of problem lies and what kind of solutions we can design. So, when you talk about micro and nano, right, what do you mean by micro and nano and how it can be useful? So, in this particular course we will be understanding several devices that we can fabricate using a technology called micro technology, right. And in particular we will focus on micro electromechanical systems based technologies as well as base sensors. This can be a microchip, it can be a flexible sensor, it can be a microfluidic chip, right. It can be a device for drug screening, it can be a device to evaluating the efficacy of the drug, right. It can be a device that can measure the weight of a fly, a house fly. So, how you can design these devices and how, what is the process for designing these devices. So, we will take each device into detail, right, and understand from a research point of view how you can use this device to solve a particular problem in clinics. So, when I talk about this kind of problems, we should understand first that where exactly we are talking about and when what exactly we are talking about. So, it is not just from clinical perspective that we can make these devices, but these devices are used in several other applications. So, if you see the slide, if you see the screen, what we see is that we are talking about 10 raised to minus 6, which is about 1 micron, to 10 raised to minus 9, which is about 1 nanometer, right. And if you talk about our human hair, right, human hair, it is around 100 microns, it is around 100 microns, you see this value, right. Average human hair thickness is about 100 microns, but we are talking about 1/10 of that, we are talking about 1 micron. In fact, we are talking about 1 nanometer, right. That means a micro means 1 millionth, right. You see 1 by 10 lakh. If I want to just say in terms of lakh, it is 10 lakh, right, 1 by 1 millionth, or if when you talk about nano, right, it is 1 billionth, right, 1 by 1 billionth. So, these are extremely small, values, and it is extremely important to understand something called recipe. Recipe or process flow. So, it is very important to understand what is a recipe and what is a process flow. So, when you talk about molecular manufacturing, what does that mean? Precision down to the atomic level, precision down to the atomic level. When you talk about nanotubes, we are talking about building advanced lightweight material as an advancement in LCD technologies. When you talk about medicine, we have devices that will flow through the circulatory system, as well as devices that can evaluate the efficacy of the drug, as well as devices that can understand and help us to screen the drug, right, as well as devices that can be used for several surgical applications. So, we will see these devices, we will focus more on this particular aspect. Then we can also use this technology, for nanocomposites, that is assisting in vast improvement in material compositions. Finally, this technology is also used in electronics. When we talk about electronics, right, we talk about MOSFETs, complementary MOSFETs, complementary metal oxide semiconductors, and how we can fabricate this MOSFETs and circuits that are used in electronics. So, you see that when you understand the concept of micro and nano, and the technology behind it, then you can apply your knowledge into several fields. It is not just limited to clinical perspective, but it can be used for electronics, it can be used for robotics, it can be used for building novel materials, it can be used for understanding the molecular manufacturing, right. So, it has a vast application, So, today's lecture is focused on showing you few devices that can be used in clinics or to solve problems which are related to medicine, alright. So, let us see, and we will talk about these devices in this particular lecture, and we will take each devices and see how it can be fabricated. So, when you understand fabrication from process flow to recipe of each device, then you can use this device by using the clean room, right, and understanding how the clean room can be used or how the equipment in the clean room should be used, so to fabricate these devices. So, let us see this slide. The first slide that you can see here, right, what are these slides? It is showing micro heaters, right. So, when I talk about micro heaters, you can see very clearly, right, that the bar is about 3 millimeter, and the width of this line is about 100 micrometers, alright. The spacing is about 100 micrometers. So, width is 100 micrometers, width 100 micrometers, spacing 100 micrometers, alright. And if you see this particular image, this is a silicon wafer, you can see, right, it is an oxidized silicon wafer, alright. And then on oxide we can, if you see this part, then it is chrome gold. What is it? Chrome gold. So, now the question is, why we have designed this particular the heater in this particular fashion, right, why we have designed the heater in this particular fashion. So, what is resistance? Resistance, if we say R equals to rho L by A, right. That means, if I want to have a resistance of a higher value, I should decrease my area and or I can increase my length. For a given metal, resistivity remains constant, right. So, here by using this design, which is a design of a coil, right, rectangular coil, we are increasing the length, and hence the resistance. You got it? We are increasing the length and hence the resistance. Okay. One thing. Second thing, where are these micro heaters used? Micro heaters are used in lot of applications such as sensors, and when I talk about sensors, these are gas sensors, Then these micro heaters are used in something called chip for antibiotic resistance. Antibiotic resistance chips. These sensors are used for microfluidics, right. So, when you say these sensors, when the sensors consist of heater and or directly heaters are used in microfluidics. Heaters can be used in a sensor that is used for antibiotic resistance. Heaters are used in sensors that is used for measuring different gases or measuring different volatile organic compounds. So, when you talk about volatile organic compound, that compounds, what does a compound means? VOC means a compound that is organic in nature and that is volatile also in nature. So, what are the example of VOCs? When you talk about VOCs, right, volatile, 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 right, organic, 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 compounds, COMPOUNDS, compounds. What are these volatile organic compounds? So, like I said, it is organic compound that is volatile, good, but can you give me an example? The example is gasoline. So, we say here petrol, it can be diesel, right, it can be diesel, it can be acetone, right, that we use in nail polish remover, it can be ethanol, it can be methanol, it can be isopropyl alcohol, it can be butanol, right. And if you want to detect these VOCs, and we will see one application, if you want to detect these VOCs, then you need to design a sensor, and this sensor, the sensing material works better at a higher temperature. So, to raise the temperature of the sensing material, we have to use heater, right, and the sensors are all micron in size, or they consist of different patterns which are microns in size, and here we have to use heaters also in micro dimensions, and that is why there is the importance of micro heater. So, we will see how we can fabricate a micro heater on an oxidized silicon substrate. The reason of using oxidized silicon substrate is that when we use silicon and directly if we deposit metal, then we will not get actual value of metal because of semiconductor, because there is a semiconductor below it, right. So, silicon is a semiconductor, we cannot deposit metal on semiconductor, right. So, we have to have an oxide layer on silicon wafer, and then on that oxide layer we can deposit a metal, and this oxide layer will act as an insulator, right. So, oxide layer acts as an insulator. So, now when we have to fabricate this micro heater, right, what are the process flow and what is the recipe, we will see in this particular lecture series. Let us see another device. Okay, let us see another device. What you see here? We see here there are interdigitated electrodes, right. It is called interdigitated. That means you have digits, this is one digit, this is second digit, third digit, fourth digit, fifth, sixth, seventh, eighth, ninth. If digits are interlocked like this, interdigitated, right, and if I measure impedance, if I measure a resistance or impedance across this, it will be infinite, correct, because there is nothing, it is not touching. But if I deposit any material on this, then I can see the change in the resistance. So, these are the electrodes that are used to measure the change in resistance or impedance of the material. So, this particular structure, if you closely see, there is a micro heater here. These are contact for micro heaters, and if you see this particular diagram, this one, you can see micro heater right over here, and then on that micro heater there is interdigitated or there are interdigitated electrodes. But again, you cannot have, let us say this is silicon, right, this is silicon dioxide, then this is the heater, heater is of metal, right, metal, so, interdigitated electrodes, this one, interdigitated electrodes also written as IDEs are also made up of metal, and you cannot have metal on metal. That means that you should have an insulating layer on which you can design interdigitated electrodes, right. So, this one is your insulating layer. So, if you see any of this device, any of this one, this one, this one, there is a micro heater at the bottom, is a micro heater at the bottom on which there is an insulator which can be a silicon dioxide or silicon nitride, on, and on that we have patterned interdigitated electrodes, right. You can see here in this particular diagram there is oxidized silicon wafer on which oxidized silicon wafer is silicon wafer with silicon dioxide, right, on which there are micro heaters or there is a micro heater. Here there is a single micro heater, as you can see, on which there is an insulator, on which there is interdigitated electrodes which are patterned using lithography. All right, and we will see the application of this interdigitated electrodes on SiO2 on micro heater in few examples later on. So, now we are complicating the design of the sensor, right. Earlier we have just seen micro heater, now we are talking about micro heater, on that another layer of silicon dioxide, another layer of interdigitated electrodes, right. So, this will get on complicating when we design complex sensors. This is very simple example, micro heater, insulator and interdigitated electrodes, but there can be more complex examples, we will see. Okay, we will see. If you go to the next slide, what we will see, another device, and this is a flexible catheter force sensors, flexible force sensors for catheter or flexible catheter force sensors for atrial fibrillation, all right. So, what is atrial fibrillation? What does atrial fibrillation means, and how we can design a flexible force sensor for such an application, right, for such an application, and what is the use of actually designing a force sensor for atrial fibrillation? We have to understand that, right. So, we will understand what exactly atrial fibrillation means, we will see how we can design a force sensor and how we can integrate this force sensor on the catheter so that it can measure the catheter contact force, all right. So, we will see how we can design this particular sensor and what kind of experiment that we can perform to understand the characteristics of the force sensor that we have designed, and this is again a medical application, right, because we are designing a force sensor for atrial fibrillation, something to do with heart, right. So, if I know microengineering, if I know microfabrication, I can design a sensor that can be used for surgical applications. You see, it is used for catheters that are used for atrial fibrillation, which is a disease in heart. So, we will see the this application. If I go to the next slide, what I can see? I can see that there are cantilevers, and if you closely see, there is a piezoresistor embedded in oxidized silicon or embedded in polysilicon, not oxidized silicon, piezoresistor embedded in polysilicon, and at the end of the cantilever, at the tip of the cantilever or at the end of the edge of the cantilever in this side, this one, there is a SU8 tip, there is a SU8 tip, right. So, this cantilever, the thickness of this cantilever is 2 micrometer, right. We are talking about human hair 100 micrometer, thickness of human hair is 100 micrometer. We are looking at a cantilever which is about 2 micrometer. And the reason of having piezoresistor is that when we press this cantilever, there will be change in resistance. That is the property of piezoresistor, right. When you apply pressure, when you apply force, there is a change in piezoresistors because of the strain created in the piezoresistor. So, because when we apply a force like this, right, it will bend in this direction like this, right. Then there is a strain in this area, strain which causes a change in the resistor embedded in the cantilever, right. Now, we can also see here in this particular diagram that there is a piezoresistive cantilever once again, which is bent, right. What is the reason of bending? Why it is bent and why this is not, right. That is because of the recipe that I was talking about, right. So, we should know what is a recipe for fabricating these devices. If the recipe is wrong, then you will have this kind of device, but what we require is this one, right. So, we will see how we can fabricate this piezoresistive microcantilever and how it can be used for several applications, including measuring the properties of tissue. Right. So, when you talk about tissue, right, the stiffness of the tissue is different. Can we measure a stiffness using piezoresistive microcantilever? That is a question, right. Can we measure the stiffness of the tissue using piezoresistive microcantilevers? And if we can measure the stiffness of tissue, then we can use this for diagnosing a case called breast cancer, right. So, we will see how it can be used for understanding the mechanical properties of the tissue. Let us go next. Now, same example, which is your interdigitated electrodes. You can see here interdigitated electrodes. And if I have an interdigitated electrode, okay, what are the applications? I told you that one application of interdigitated electrode would be measuring the resistance or impedance. So, when you talk about resistance or impedance, you require some material to be kept on the interdigitated electrodes, right. So, if we keep a tissue on the interdigitated electrodes, what we can measure? We can measure impedance. Why? Because there is a solution required to keep the tissue alive, right, and that is PBS, okay, the silent solution. So, if I have interdigitated electrodes and on that if I place a tissue on which I have a solution, then I cannot just measure resistance, right, because there are several parasitic components that comes into play such as double layer capacitance, right. So, now instead of measuring resistance, what I will measure? I will measure impedance, I will measure impedance of the tissue. So, now if your device or if you can design a device that can measure the impedance of tissue or it can measure impedance of cells, as the disease progresses, then you are measuring the electrical property of tissue or cell, is not it, right. So, what we will do by measuring electrical property of tissue? What we did by measuring mechanical property of tissue, same thing we will do by electrical property of tissue. That means that if I can see the change in the tissue properties as the disease progresses, and let us take an example of a breast cancer or oral cancer or any other cancer related to tissue, and my sensor can give these changes, can measure the signature, can measure the electrical and mechanical signature of the tissue or of the cell, I can diagnose, I can use this device as diagnosing device for the cancer, right. So, now we are using interdigitated electrodes without any heater for understanding the properties of tissue, and these are the electrical property of tissue. But when I talk about electrical property of tissue, right, I need to first have interdigitated electrodes, and when I talk about that this tissue is there, we have to load a PBS, that is a solution, right. Then if I load this solution on the glass slide, it will not stay on the point, right. So, we have to create a well to hold this solution, So, we will see how we can create this kind of device, that is a interdigitated electrodes within an SU 8 well. That is another device that we can design from the biomedical application, from the clinical perspective, right. So, this is what we can see here on the slide. This is, you can see that the tissue is placed on the interdigitated electrodes, and you can see here the interdigitated electrodes are fabricated using chrome and gold, and the spacing and width, the width and spacing of this interdigitated electrodes is 10 micron, and the well is made up of SU 8, well is made up of SU 8, right. So, we will see how we can use this kind of device for measuring the tissue property, particularly electrical property of tissue, okay. Let us move to next slide. Now, we will also understand how we can design a tool that can be used for diagnosing cancer. And to understand the designing of this tool that can be used to diagnose cancer, we again need the basic understanding of what we call microtechnology, right. So, here we will be understanding or we will be studying several modalities. When I say several modalities, one is mechanical, another is electrical, another is thermal. Mechanical, electrical, thermal. Thermal properties, all three properties of a tissue if I want to measure, can I design a sensor that can measure all three properties, or can I design a biochip that can measure all three properties of tissue. When I say all three properties, the electrical properties, mechanical properties, thermal properties, and I do not only want to design the biochip, but I also want to integrate this biochip in a tool such that when the tissue is out, the tissue is taken from the biopsy, we will see how the tissues are taken out. Once the tissue is out from the biopsy, I can place the tissue on this tool and I can just press a button, or the pathologist, if it is in pathology lab, the pathologist will just press a button and he or she will be able to see what are the changes in the tissue properties, and thus this can be a aid to the surgeon. This device, this tool can be aid sorry, this can be a aiding tool to the surgeon, right. So, why we require aiding tool for the surgeon? Is the gold standard not enough? Right now, how cancer is diagnosed? Right. So, we have to understand these things, and then only we can design a particular tool that can be used for understanding the tissue properties. So, now we will see as you see that right starting from the micro heater, then we came to interdigital electrodes, then we make to cantilever, and then we went to interdigital electrodes within SU812. Now, we are talking about one more sensor that can be integrated, and that is thermal sensor. So, thermal sensor can be micro heater, we can use micro heater for thermal sensing. We had to use the piezoresistive material, that is the we can use any piezoresistive material, example is P dot PSS, which is a conducting polymer, and then we have to use electrical sensor to measure the tissue properties. So, all three sensors integrated on a biochip. How we can do that, right? How we can do that. So, we will see in this series of lecture how we can fabricate such kind of device, all right. Now, let us see another device, and this device is used for drug screening, right, drug screening. So, how we can design this drug screening device, and what is the use of this drug screening device, right. So, right now if a patient has to be given a particular drug, which drug would be more effective from a patient point of view, right. Every drug and every patient responds to the drug in a different way. So, can we design a device that is patient centric? What is it? Patient centric, right, such that we take the cells from the patient and we load in the device, and we pass different drugs next to these cells and see the response of the cells or tissue with respect to different drugs. Then we can understand which drug is more effective. So, to measure this response, either we can use impedance or we can use the fluorescence technique. Fluorescence technique right now is used in biolabs, right. So, what I was saying, that if I take a cell, let us say if I take a cell from my hand, let us say from here, right, I take a tissue, I place the tissue in the microfluidic chip, right, I slice the tissue, place the tissue in microfluidic chips, pass the drug, and if the drug is effective, tissue will start dying. That the death of the tissue, if I can measure by using some sensor that is integrated within this microfluidic chip, right, then I can understand which drug is more effective for my body. Now, we are not talking about just if I get sick and I have to take out the tissue, right. We are not talking about that kind of device. We are talking about device when it is cancer, and when the drug that is administered to the patient or drug that is given to the patient is extremely important, because it is a matter of life and death, right. Which drug will be more effective and which not, because every patient will respond differently. So, now as an engineer, as a microengineer who knows microengineering and microtechnology, can you design a device that can be used from patient centric point of view for rapid drug screening? You get it? So, we will see how you can design this device, right. So, that when we use this device, then based on the result a proper drug can be given to a proper patient, and it may change from patient to patient, right, thus making the delivery of drug, thus making the screening of the drug more effective, all right. So, if you see the screen, what we see, that there is a micro heater, right, on which there should be an insulator, on which there are electrodes, and this everything. So, this one and this one should be on one chip, and for flowing I need a channels. These channels I can fabricate using soft lithography, soft lithography, all right, and the material that you can see here, this material, right, that cube is PDMS, the material is PDMS, right. So, can we design a tool or can we design a device that can be used for rapid drug screening. So, we will see this device, how we can fabricate this device and how it can be used. What are the preliminary results that I obtained using this particular device. Similarly, these are all research problems, you can work on this, you can design these devices. By understanding this, what we are understanding, we are gaining expertise or we are understanding or we are improving our knowledge for designing several sensors that can be used from research point of view, right. Can you do some kind of research by gaining this experience from this course, right. That is the idea of this particular course. Okay. At least you know the process flow. Once you know the process flow, when you go to clean room for fabrication of the device, you will not be like blank, you will know, okay, this devices or this equipment is used for this particular device. We will also see kind of equipment that are used for fabricating device, not only process flow and recipe, all right. So, if I go to next slide, and next slide is for antibiotic susceptibility. We will see how we can design, right, a microchip that you can see here, right over here, for understanding antibiotic susceptibility. Now, what does that mean? What does that mean? Right, and we can also design a microfluidic chip for understanding the antibiotic susceptibility. So, if you ever went to doctor, right, if you went to doctor and you have some kind of infection, right, the doctor will generally prescribe topical antibiotics, that is 3-4 antibiotics to eat, right, and we take this medicine, we eat and we pay doctor, right. Why to eat 3-4 medicines? Why not one, right? Why not one? Why to eat 3-4 topical antibiotics? Because first, which antibiotic would be useful, we do not know, right. Even we know that this is a bacterial infection and this infection is due to particular bacteria and there are medicines, antibiotics meant for killing those bacteria, still we have to take 3-4 antibiotics because we do not know which antibiotic would be useful for killing this bacteria, or will the bacteria would be having a resistance against antibiotic, we do not know, neither do the doctor, right. So, one is we are given the antibiotic, second is our blood is taken or a urine sample is taken for further understanding what bacteria, and suppose bacteria is known, what antibiotic to give. And the results from the pathology comes in 24 to 48 hours, 24 to 48 hours, in some cases even more, some cases even more time is taken for giving you the results. Okay, this antibiotic would be more effective with this particular bacteria since the patient is suffering from this particular disease, right. It is known, like if I have a urinary tract infection, then I know that the E. coli, that is bacteria called E. coli, would be in higher concentration, right. But which antibiotic to use, that will a doctor can generally understand based on the reports from the path lab. Now, it is okay, I do not say that the current way of medicine is wrong, it is what it is, this is what we know, right. But the idea is why we cannot reduce this time, why we have to wait for 24 hours, why we have to wait for 48 hours to get the report. Can you design a device that can perform the analysis within a shorter period of time by requiring a lesser sample. Why I have to give like 10 ml of blood or even 20 ml of blood or even 1 ml of blood? How about microliters? How about similar to glucometer? I just puncture and that is it, that is enough for me to give, right. So, reducing the sample size, rapidly getting the diagnosis and giving a correct antibiotic to the patient, not correct, these are all are correct antibiotics by the way. The antibiotic that will be effective for this particular bacteria. If we can do this whole thing within a shorter period of time using a device, then that will be really awesome, is not it. Now, again you understand from our point of view, if I have a bacterial infection, if a doctor gives me antibiotics, I can take antibiotic and wait for 2 days. Even this antibiotic, one of the antibiotic is useful, another one is not, my immune system can take it. But what about neonates? What about babies? Right? There are lot of bacterial infection in neonates and the immune system of a baby is extremely weak. So, in that case waiting for 24 to 48 hours may cause a death or life threatening issue for a neonate. Thus, this kind of device that can do a rapid testing of antibiotic medicines, right, or antibiotics and can tell that the bacteria is resistant or not, it is extremely useful, right. So, for that we will see how we can design a microchip or a microfluidic device, alright. So, that is what we see on this screen, a microfluidic chip for rapid bacterial antibiotic susceptibility testing. Alright, we will see this device, how we can fabricate this device. Now, I go to another device, and these are microfluidic chip. Again you can see is a microfluidic chip. These are SEM images of microfluidic chip, and this is just a mold, image of the mold that is made in silicon. And we will see why we have made this mold in silicon, what is the use of this device, we will see everything. Okay. So, what is the idea? The idea is that if I want to understand that which drug can be used for killing this cancer, suppose this is a cancerous tissue and you can see here vessels, right, blood vessels supplying oxygen and nutrition to the cancerous tissue, supplying oxygen and nutrition to the cancerous tissue, and then you can see here there is a extracellular matrix, alright. So, I want to test a drug that will start or stop, that will stop growing of these vessels. If the vessels are stopped, if the growth of vessels are stopped or the vessels are destroyed, right, the vessels that are providing nutrition and oxygen to the tumor are destroyed, right, then what kind of drug would be effective or what kind of combination of drug would be effective? What kind of, suppose there are 3 drugs 1, 2 and 3, one will be effective, second will be effective or third will be effective, or combination of 1 and 2 will be effective, or combination of 2 and 3 will be effective, or combination of 1 and 3 will be effective, or combination of all 3 will be effective, right. If I want to study this combination, or we call combinational therapy, what we call combinational, COMBINATIONAL, combinational therapy, alright, combinational therapy. Then what can I do? I can design a microfluidic chip that mimics the same thing and I can test different drugs. I can test different drugs whether drug is effective or not, that is drug efficacy, whether drug is effective in killing the tubules or in destroying the vessels that are supplying oxygen and nutrition to the tumor. If the nutrition and oxygen is stopped, then the tumor will start dying, because tumor is nothing but group of cells growing abnormally, right. So, this is another device that we will be looking at from the clinical perspective. Then we go to the next slide, all right, and this is very interesting application of flexible MEMS, right, flexible micro electromechanical sensors or MEMS based systems based sensors for phenotyping or understanding tissue properties, all right. And we will see how the process flow happens, how this device looks like. If you see closely, this device has this particular pattern, right, and actually there are array of these patterns, all right, and these arrays are nothing but strain gauge. What is that? Strain gauge. What is the use of strain gauge? Strain gauge is nothing but when you apply strain, it will change in the resistance, it is a kind of piezo resistor. So, I can make this array of sensors using P dot PSS. P dot PSS is a conductive polymer. What is it? Conductive polymer, that is conductive. All right, one. Second, if I have an insulator on it, insulator on this, right, and on insulator if I have gold pads, you can see here gold pad patterns, and by the way, everything that you see here, like here in the center, consists of piezoresistor and gold pad and SU8 pillar. It is right here, you see, so tiny, super tiny. You see, this is 1 millimeter. 1 millimeter. So, it is about 1 millimeter. Within that area we have the sensors, okay. So, anyway, coming back to here, if I have piezoresistors on which I have an insulator, on which there is a gold pad, and on gold pads there are SU8 pillars, then I have a sensor. If the substrate is flexible, then I can use these sensors, right, and SU8 pillar we can make it conductive, I can use this sensor for measuring the electrical and mechanical property of a material, and we will see how. We can use this device for measuring the electrical and mechanical property of the material. And you can see here the contact pads, you see it is like zigzag, right, it is like here, it is not straight line. Why to have this kind of pattern? Why not to have straight line? What is the designing problem in this one or this one? Why we have selected this particular design? We will see that as well. So that you understand that how you can design this kind of flexible sensors, right, for your particular application. Because you see, I am showing some of the application of my work, my research, right. But what about the problems that you come up with? If you come up with a unique problem and you want to find a solution for that particular problem, you have to design your own sensors. By understanding these flexible sensors, what we were talking about, right, can you use a concept and can you create your own sensor? That is the idea, all right guys. So, what I will do is I will teach you how to fabricate these flexible sensors using the MEMS technology, all right. So, there are few more devices that we have to see, and those devices we will see in the second module, right. This is an introductory module where I wanted to you to get familiarized with lot of devices, different kind of sensors and MEMS based technology, right, and how these sensors or devices or microfluidic chips can be used for clinical perspective, from clinical perspective actually, right. So, but please make sure or please understand this thing, that this is not only one area where you can use the knowledge of microengineering. We will see the fabrication, and you can use this fabrication for designing sensors for other applications as well, right. So, I will show you devices that are used for clinical perspective, but you can make a devices which can be used for electronics, which can be used for robotics. For example, if I want to have a touch sensor, a robot wants to have a touch sensor. Can you design this touch sensor using the knowledge that you acquire in this subject? That is the idea, alright. So, we will be looking at from that point of view as well, that if I want to design a flexible force sensors or a touch sensors, what kind of changes in the design can be, alright. So, I will see you in the next module. We will discuss few more devices, and then we will start understanding microfabrication. We will see the process flow, how you can design a device, what are the techniques used for designing this device, such as what are the equipment used, how a clean room looks like, what are the equipment within the clean room, and then we will see each device in detail and how it can be used for solving a particular problem. Alright. Till then, you again just look at the lecture. At the end of this particular course, you will be understand you will understand how you can fabricate a device, at least using the process flow, at least on paper. And then in the next course, I have a plan to go to the fab lab and perform actual experiments. But to go to that level, first we need to understand how we can fabricate devices, or how we can design the process flow and recipe for the device. Alright. So, I will see you in the next class. Till then, you take care.